Good afternoon, sir.
Afternoon. Okay. Shall I start? Okay. Today I shall discuss about some section of reinforced concrete beam section in working stress method. So first of all, just recapitulate the previous all those things briefly. Suppose we have a simply supported beam. Today I use the black digital board. Is it okay for you?
Okay, sir.
Okay.
Yes, sir.
Hello. Okay. Now we apply some load here, and we know this is the bending moment diagram, and we have to take the maximum bending moment. Okay. M. This is the maximum bending moment. Now this is external bending moment, maximum bending moment, and this is also external. This bending moment is also due to the external load. Okay. Now what we have done previously, we have equating this bending moment with tension force or compression force or tension force multiplied by lever arm. Okay, multiplied by lever arm. Now the theoretical section, this is the theoretical section. So this is the neutral axis, and this is the tension zone, and we have to neglect the concrete here. We have to just consider the reinforcement here. Okay, so at this position there is some reinforcement. Okay, now previously you know that the relation between stress of concrete and stress of steel. What is the relation between the stress of concrete and stress of steel? What is the relation? Sigma C or sigma CBC, I should say, sigma CBC equal modular ratio M multiplied by sigma ST. Okay, this is one relation, and another relation is area of concrete equals to modular ratio multiplied area of steel. Okay, and another parameter is that suppose this is the width of the beam B, and this is effective depth of the beam. Okay, and this is suppose overall depth, capital D. So capital D minus clear cover is equal to, or effective cover is equal to effective depth. Okay, and the depth of the neutral axis is nothing but KD. If we can calculate value of K, then we can multiply the K value with depth D, and we can get the neutral axis depth KD. Okay, and this is the effective depth. Okay, now if I want to calculate a value of K, I can go with I can use two methods. One method is taking the moment of area about the neutral axis. Taking the moment of area about the neutral axis. Okay. Now, what is the area? Area of compression zone. Okay. This is the area, and area of tension zone. Please keep in mind, area of tension zone means only area of reinforcement. Okay. So if I take moment of area about the neutral axis, so total area of concrete is B multiplied by KD. B multiplied by KD. This is the total area of concrete. Okay, in compression zone. And if I multiply it with the distance, then we can get moment. And what is the distance? Distance is the C distance. We can assume that the total area is concentrated at the CG point of this area. Okay, suppose this is the CG, and this distance is nothing but half of KD. Okay, this is KD by 2. Okay, now this distance is KD by 2 equal, and this area is MAST. Why it is MAST? Previously we derived this formula, AC is equal to MAST. Okay, but why we have to consider this area is AC? Why? Because if I consider two materials simultaneously, we cannot calculate anything. Okay, stress or area like that, we cannot calculate all those parameters. So what we have to do, we can replace the reinforcement by concrete. Okay, and how we can replace the reinforcement by concrete? We have to apply the concrete in such a fashion that the load, suppose this area of the steel, suppose this area of the steel is subjected to some load. Okay, some load, suppose P is the load is applying on this particular reinforcement of this section. Now we have to apply that much of concrete which can carry this amount of load. Okay, now suppose this is the area of reinforcement that can resist P load, Okay, now if I say that we are going to apply some concrete here by replacing the steel, then the amount of concrete will be very high. Okay, so this amount of concrete can resist P load. You got my point? So this is AST and this is AC. Why the area of concrete is so high? Because concrete cannot resist tensile load, that much amount. That's why we have to apply large amount of area to resist the preload. Okay, so we just replace the reinforcement here. We just replace the reinforcement by some amount of concrete. Okay, now what is the actual theoretical cross section is that, suppose this is the neutral axis and here suppose this is the concrete here, which can resist the load equal to that load resisted by the reinforcement. Okay, this is the clear cover. Now this area is this B into KD. Okay, and this area is M multiplied by AST, because actually the area is AC. Okay, and we know that AC is equal to M into ST. That's why we are considering this in terms of AST. So this is M into ST. Now if I take the moment, so this area is M multiplied by AST, and if I take the moment, then the distance should be the CG of this point to the neutral axis. This should be the distance. Okay, so this is the distance, and this distance equal to nothing but D minus KT. D minus KD. Okay, so this is the formula of taking the moment about the neutral axis. So let me again draw it. No issue. So this is our section. This is neutral axis, and at the bottom this is concrete, and area is M into ST, and this is the cover. So this is M into AST, this distance is B, and this distance is KD, and this distance is D minus KD. So our formula is B multiplied by KD. This is the area. This is the area, and multiplied by KD by 2. Equal again area MST multiplied by distance D minus KD. Okay.
স্যার কেডিটাকে তো এক্স এও ধরা যায়, অ্যাকচুয়াল ডেপথ অফ নিউট্রাল এক্সিস।
XU actually we generally use this term in limit state method. Okay, in work list method we use the KD term. Okay.
Okay.
Now, if I simplify this formula, you can see B and D will eliminate. Okay. Now, B K square D square by 2 equals MST D minus MST KD. So now I have to change the ST. I have to change the ST in terms of percentage of steel. Okay. So percentage of steel, suppose we are considering the B multiplied by D is the total area of the concrete section. Okay, the beam section, B multiplied by D. And if I consider this is 100%, if I consider this is 100%, then ST will be 100 by BD into ST, this percent. Okay, if BD is 100%, then ST will be total 100 ST by BD. This is the percentage, and generally we call this as a P percent. Okay. So actually, so P equals, we can say P equals ST by BD. P equals ST by BD. So AST equals P BD. Okay, AST equals P BD. Now just place all those terms. M P B D square minus M P B K D square. Okay, so this formula, if you simplify, then you can get the simplified formula is K square minus 2K MP minus 2MP equals to 0. Okay. Sorry. One minute, okay? Now the formula is K square minus 2MP sorry 2 mpk minus 2 mp equals to 0. So we can write this formula in this way: minus 2k mp minus 2mp plus m square p square minus m square p square equals to 0. So k square minus 2k mp plus m square p square minus 2mp minus m square p square is equal to 0, or we can say equals plus 2mp plus m square p square. Okay, so this is nothing but k plus mp whole square, sorry, k minus mp whole square okay, I think I have a mistake. This is actually k square plus 2mp. Okay, this is k square plus 2mp. So k plus mp whole square equals two mp plus m square p square. So k plus mp equals over root of m square p square plus 2mp, and finally k equals m square p square plus 2mp minus mp. So this is the formula of k. Okay, now suppose you want to calculate the neutral axis depth in working stress method. So what you can do, you just suppose reinforcement is given here, so you calculate the area of reinforcement, AST, then you can calculate P and AST by BD, and that is modular ratio. What is the formula of modular ratio? Modular ratio is, code is given you, modular ratio is equal to 280 by 3 sigma CBC. Okay, this is the modular ratio. Now you can calculate k, and if you multiply the k with d, k with d, you can get the neutral axis depth. Okay, nothing else. Now you have to calculate the lever arm. What is lever arm? Suppose this is the section, and this is the stress diagram. Okay, this is the stress diagram, and this is the maximum stress, sigma CBC, and this is the maximum stress in terms of concrete, so sigma st by m. You know that the sigma c is equal to sigma st by m. So this is actually, we place the reinforcement by concrete. We replace the reinforcement by concrete. So this is actually transformed section. This is called transformed section. Okay. Now the compression force C, we can assume that this compression force will act through the CG of this triangle. Okay, CG of this triangle, and this distance, I have said you, this neutral axis depth is KD, and this distance is nothing but 1/3 of KD. This distance is 1/3 of KD. So what is the lever arm distance? This is T and this is C. So this distance is lever arm. Okay, so this is nothing but total distance from bottom fiber to tension, total distance, that is D, minus 1/3 of KD. So we can say lever arm is equal to total distance D minus 1/3 of KD, and D multiplied by 1 minus K by 3. So generally we said that this is JD. So J equals nothing but 1 minus K by 3. Okay, J equals nothing but 1 minus K by 3. So now the all the total section, you are this is clear to you that all the parameters you know and formula you know. That is, let me draw this section again. So this is the section, this is the concrete transformed section, this distance is width of the beam, total depth of the beam is D, and this is effective depth, this is B. Okay, this distance is KD, neutral axis depth, and lever arm this is JD, and JD is equal to D into 1 minus K by 3. Okay. Okay, and the maximum stress is sigma CBC, and maximum stress here is sigma ST by M. Okay. You can calculate the K value. Previously I have calculated the K value from this section. Okay, from this taking the area of this section from this section, taking the area about the neutral axis, taking the area moment of area about the neutral axis in compression side and also in tension side. Now you can calculate the K value from the stress diagram also. This is the stress diagram, so you can calculate the K value from the stress diagram also. How you can calculate? Now you have to take the you just calculate the compression force here, compression force, and you just calculate the tension force here. And if you, we know that C always equals to T. Okay, C always equals to T. Now if you can calculate C and if you can calculate T, then you can get also the K value. Just let me show the things. How we can calculate the C value from the compression zone? You can remember that this diagram is not two-dimensional diagram. This is actually a three-dimensional diagram. Okay, so if I draw the three-dimensional figure, this will be the three-dimensional figure. Okay, now this distance is sigma CBC. This distance is sigma CBC, and this distance is B, width of the beam. Okay, and this distance is neutral axis depth, KD. Now if you want to calculate a total volume of this three-dimensional figure, what you can do, you just calculate the area of this triangle, area of this triangle, and multiply it with B, multiply it with B, then you can get the total volume. So area of this triangle means nothing but area of this triangle. Okay, this triangle. So area of this triangle is sigma CBC multiplied by KD into half. So half sigma CBC into KD. This is the area. Okay, this is the area of this triangle, and multiplied by B. That means total volume of this figure, three-dimensional figure. This is actually C. And what is T? T is nothing but area multiplied by stress, and stress is sigma ST. Stress is sigma ST. Okay. Now this sigma ST you can replace by sigma CBC. You can replace by sigma CBC, and then you can get the K value. The formula is same. K is equal to, you can get this M square P square plus 2MP minus MP. Okay, now I am not going to details with this because this is actually the another method to calculate the k value, nothing else. Okay, you can use any method. Okay, now the next thing is that we have a bending moment applied. We have a external bending moment due to the applied external load. Now this bending moment is equals to C multiplied by lever arm, and C is equal to, previously you know that C is equal to nothing but half sigma CBC K D, this is the area, multiplied by B, that means the total volume of this three-dimensional stress block. Okay, and multiplied by lever arm. Lever arm is JD, and we can say that this is D multiplied by 1 minus K by 3. D multiplied by 1 minus K by 3. So this is the moment coming from concrete. This is the moment coming from concrete. Okay, let me keep this J, it will be better. J. So we can say this is half sigma CBC J K B D square. Okay, half sigma CBC J K B D square, and it is coming from concrete. And another part is equals to T multiplied by lever arm, and T is nothing but stress multiplied by area sigma ST AST. AST is area of steel, and JD. Okay, so this is coming from tension side. Now the another term will come here, that is moment carrying capacity or moment of resistance. What is moment of resistance? Okay, you know what is bending moment, you know what is stress of concrete, you know what is stress of steel, what is neutral axis depth, what is lever arm, all those things. You what is area of reinforcement, all those things you know, all parameter. But new term will come here, that is moment of resistance. What is moment of resistance? To understand this, just you have to think what is happening at the time when we are gradually applying the load. Okay, now we have to notice all those change of all those parameters simultaneously. That means when we apply the some load on a beam, what is the change in deflection, what is the change in bending moment, what is the change in stress in concrete, what is the change in stress in steel, and what is the change in stress strain curve of concrete, and what is the change in stress strain curve of steel. You have to look into all those parameters simultaneously, otherwise you cannot understand what is happening actually. So suppose we have a simply supported beam. We have a simply supported beam and we are applying the load gradually. Suppose 0, 1, 2, 3, 4 like that. Okay, 5 like that. We are gradually applying. So what will happen? First of all, when the load is in one position, then suppose this will be the deflection. Okay. Now bending moment, suppose this is the bending moment, figure of this bending moment, suppose, and the bending stress diagram will be suppose like this. So this is the neutral axis, this is the bending stress diagram. Okay, and this is the sigma c. Why I say sigma c and I did not say the sigma cbc? Okay, please keep in mind there is a difference between sigma c and sigma cbc. Previously I show you that sigma c is actually nothing but sigma cbc, but there is some difference. What is the difference? Now you can understand. This is sigma cbc, sigma c, and this value is sigma s, not sigma st. Okay, now look at this diagram. This is suppose stress strain curve of concrete. Okay, this is strain, this is stress, and suppose this is stress strain curve of steel. This is for concrete, this is for steel, and both are linear. Okay, because this is the one assumption of working stress method. So this is strain, and this is stress. Okay, now when we are in number 1 position in this load, suppose this is the bending moment, suppose this is bending moment 1. Okay, now this in this stress diagram, this is stress diagram. Okay, this is stress diagram. Sigma c1 and sigma s1 will develop to resist this m1, okay, and this sigma c is this value sigma c1, and this s1 is this value sigma s1. Okay, and when we apply, we are in second position, that means we increase the load. Suppose this is the deflection, so this is the bending moment at the second stage. Okay, and this is the Next, bending stress diagram. That means the bottommost and topmost fiber have the maximum stress. Now suppose this is sigma C2 and this is sigma S2. Okay, and in concrete, suppose this is sigma C2 and this is sigma S2. Okay, and the IS code, please keep in mind, IS code is IS code provides you this diagram and this diagram. Okay, these two diagram IS code provides you in terms of table 21 and table 22. So this is table 21 and this is table 22. I will take some few 10 minutes, okay, to complete this. Don't worry. Table 21, table 22 give you this this data. Okay. Now IS code says that you cannot go beyond this limit, and this is the permissible stress. This is called permissible stress, and this is the final. That means the final stage of sigma C. This is called sigma CBC. Okay, and this is the final stage of stress in steel. This is called sigma ST. Okay, now when we are in 3, 4, 5 position, suppose we are in final position, this is 5. Okay, 5. Now this is the maximum final bending moment. The picture is not clear, but you just imagine this is the maximum deflection, nothing else. Okay, so this is the final bending moment and final deflection. This is the final bending moment. Okay, so we can say this is the maximum bending moment, and at that time concrete develops its maximum stress sigma CBC and steel develops its maximum stress sigma ST. Okay, so this value is sigma CBC. Okay, that means this value concrete reaches its ultimate stress. This is the stress line in y direction in stress strain curve of concrete. So concrete reaches its ultimate stress sigma CBC and steel reaches its it is not ultimate, I should say it is permissible, sigma ST. Okay, permissible stress sigma ST. Okay, so what is actually happening, the limitation of sigma C and sigma ST is there, that is the limitation provides by IS 456, and when we are going to apply the final load here, then due to applied final load there is the final bending moment. Okay, and this bending moment will resist by developing the maximum stress in topmost fiber and maximum stress in bottommost fiber for concrete and steel. Okay, and when this curve, actually what is happening, this curve is rotating clockwise direction, you can see. Okay, this curve, this line is rotating in clockwise direction about the neutral axis, Okay, so this curve is called stress line. This line is called stress line. Okay, this stress line is actually rotating in clockwise direction when we are going to increase the load gradually. Okay, now how much it will rotate? It will rotate up to that limit when the IS code IS code provides the ultimate limitation of stress of concrete and stress of steel, that is sigma CBC and sigma ST. Okay, so you can see this stress line is rotating in clockwise direction, and simultaneously concrete and steel both reaches the maximum stress, that means sigma CBC and sigma ST, and this section is called balanced section. This section is called balanced section. Okay, so what is balanced section? Balanced section is when our strain line, when the strain line is simultaneously reaches the stress of concrete and stress of concrete and stress of steel simultaneously, then this section is called a balanced section. So this is ST and this is sigma CBC. Okay, and you can see it is gradually increasing from this position. This is the second position, this is the third position, this is the say fourth position, this is the final fifth position. Okay, so already there is the limitation of sigma CBC, there is the limitation of sigma ST. Okay, so this limitation, this line can touch the strain line and simultaneously, and this section is called we called it balanced section. Okay, and if you want to continue, then I don't have any problem. I shall continue. Another two section is there, under response section and over response section. Shall I continue?
No sir, 3:30 PM থেকে আছে ল্যাপলাস আছে ট্রান্সপোর্টেশন.
Okay, then I stop here. Next day I shall discuss what is
next week Monday.
Okay, next week means next day means next week. So I shall discuss about what is under response section, what is balance section. Okay, now you tell me, up to this, is it clear to you?
Yes sir.
Huh?
Yes sir.
Yes. Okay, so
Attendance.
Ronit Das, you are presenting your screen. Ronit, আচ্ছা তোমরা কি সবাই আমার স্ক্রিনটা দেখতে পেয়েছো লাস্ট পর্যন্ত? কারণ
আমি
রনিত নিজের স্ক্রিনটা শেয়ার করছে, সেই জন্য আমি বললাম।
না দেখা গেছে।
দেখা গেছে, আচ্ছা ঠিক আছে।
আমরা স্যার যে প্রেজেন্টেশনে ক্লিক করব সেটাই তো দেখতে পাবো, অন্য কেউ করতেই পারে স্ক্রিন শেয়ার আমাদেরকে।
হ্যাঁ হ্যাঁ।
ও আচ্ছা, তোমরা যেহেতু
যেটা পিন করব সেটাই দেখতে পাবো।
ওকে, তোমরা আমার যেহেতু স্ক্রিনটা পিন করে আছো, অন্য কেউ প্রেজেন্ট করলে তোমরা দেখতে পাবে না, তাই?
হ্যাঁ।
ওকে ওকে, ঠিক আছে তাহলে। ওকে
স্যার ওয়ার্কশিটের মেথডে স্টেপটা পাবো?
হ্যাঁ হ্যালো, কি বলছো?
ওয়ার্কশিটের মেথডে পিডিএফ পাবো? পিডিএফ
আরেকবার বলো, কথাটা কেটে গেল।
কি বলছে? পিডিএফ এর কথা বল।
পিডিএফ? এটা কিসের পিডিএফ?
আমি বলি, অন্য কেউ বলে।
দাঁড়াও, যে বিবেক রয় বলছে, বিবেক রয়কে পরিষ্কার করে বলতে দাও এটা কি বলছে।
স্যার বলছে ওয়ার্কিং স্টেট মেথড আর লিমিট স্টেট মেথডের পিডিএফটা পাবো?
পিডিএফ বলতে মানে তুমি কোনো বইয়ের কোনো পিডিএফ চাচ্ছ, না আমি যেটা দেখালাম সেরকম কিছু চাইছো? হ্যালো বিবেক।
স্যার বলছি বইয়ের হলে ভালো হয়।
আমি তোমাদের অলরেডি 3টে বই দিয়ে দিয়েছি। ওকে, 3টে বই দিয়ে দিয়েছি, এবং তার সাথে আমি তোমাদের গুগল ক্লাসরুমে পিডিএফও দিচ্ছি।
হ্যাঁ দেওয়া আছে, দেখেছি।
সেগুলো তোমরা দেখতে থাকো, আর ওগুলোর মধ্যে অনেক কিছু আছে, ঠিক আছে। আর ভিডিওগুলো, এই ভিডিওগুলো তোমরা ইউটিউবে দিয়ে দিচ্ছি তোমাদের, পরে তোমাদের যখন যেটা প্রবলেম হবে তোমরা ভিডিওগুলো দেখে নিতে পারবে, অসুবিধা নেই। তো তারপরেও যখন প্রবলেম হবে তোমরা আমাকে বলবে, আমি সেটা নিয়ে ডিসকাস করবো আবার। ওকে, নো প্রবলেম। তোমাদের কাছে, তোমরা যেন পুরো জিনিসটা যেন তোমাদের কাছে ক্লিয়ার থাকে। ওকে, কোনো ডাউটে যেন না থাকে। ওকে, তোমরা
Okay.
কোনো রকম ডাউট রাখবে না। ওকে, যখন
Okay, sir.
যেখানে যেটা প্রবলেম হবে তোমরা সেটা আমাকে বলবে যে এটা প্রবলেম হচ্ছে। এই রনিত দাস, তুমি প্রেজেন্টেশনটা অফ করো তো, প্রবলেম হচ্ছে। রনিত দাস কি শুনতে পাচ্ছে? হ্যাঁ, থ্যাংক ইউ।
অ্যাটেন্ডেন্সটা নিয়ে নাও।
হ্যাঁ, অ্যাটেন্ডেন্সটা নেব। আচ্ছা, সবাই কেউ কি লেফট হয়েছে এখনো আসেনি?
হ্যাঁ, সবাই আছে,
সবাই আছে তো?
31 জন আছে।
33 আছে। 33 বেশি?
আমরা স্ক্রিনটা নিয়ে হবে
33 বেশি ছিল নাকি 33 ছিল?
ওরকমই ছিল।
ওকে, এক মিনিট, এটা একটু দেখে নিই। হ্যাঁ, ঠিক আছে, ওকে, হয়ে গেছে।
ঠিক আছে স্যার, লিভ করবো।
হ্যাঁ হ্যাঁ, leave করো।
ঠিক আছে।
থ্যাংক ইউ স্যার।